Corrosion can destroy pipelines, tanks, ships, offshore structures, and buried steel equipment. But here is the interesting part. We can slow it down, and in many cases control it, by using electricity. That method is called cathodic protection. In this video, we will explain cathodic protection from zero. We will cover what corrosion is, why metal rusts, how coatings protect steel, why coatings are not enough, and how cathodic protection works as the second line of defense. We will also compare the two main types, galvanic cathodic protection and impressed current cathodic protection, also called ICCP. By the end of this video, you will understand the basic idea behind one of the most important corrosion protection methods in industry. Let's start with corrosion. Corrosion is the natural process where metal returns to a more stable form. For steel, that usually means rust. Steel is made from iron. During manufacturing, energy is used to turn iron ore into steel. But when steel is placed in soil, seawater, concrete, or moisture, nature tries to reverse that process. The steel wants to go back to an oxidized state. That is corrosion. In simple words, corrosion is metal slowly losing itself to the environment. Now here is the most important idea. Corrosion is not just a chemical reaction, it is an electrochemical reaction. That means corrosion involves both chemistry and electricity. For corrosion to happen, four things are usually needed: a metal, an anode, a cathode, and an electrolyte. Let's explain these one by one. The metal is the steel pipe, tank, or structure. The anode is the area where corrosion happens. The cathode is the area where corrosion does not happen. The electrolyte is the conductive environment around the metal, such as soil, seawater, or wet concrete. In a buried pipeline, the soil acts like an electrolyte. In a ship, seawater acts like an electrolyte. In a storage tank bottom, moisture and soil can act like an electrolyte. So, corrosion is like a tiny battery forming on the surface of the steel. Some areas become anodic, some areas become cathodic. An electrical current starts to flow. At the anodic area, metal atoms leave the steel surface. For iron, the basic reaction is iron becomes iron ions and releases electrons. In simple terms, the steel gives up part of itself. That is where metal loss happens. That is where pits form. That is where wall thickness decreases. And that is the dangerous part of corrosion. So remember this. Anode means corrosion. Where the steel is anodic, the steel is being consumed. The cathodic area is different. At the cathode, the metal does not dissolve. Other reactions happen there, but the steel itself is not being consumed in the same way. So in corrosion language, the anode corrodes. The cathode is protected. This is the key idea behind cathodic protection. If we can force the entire structure to behave like a cathode, corrosion can be greatly reduced. And that is exactly what cathodic protection tries to do. Before we talk about cathodic protection systems, we need to talk about coatings. For pipelines, tanks, ships, and many other steel structures, the first defense against corrosion is usually a protective coating. The coating acts like a barrier. It separates the metal from the environment. If the soil, water, oxygen, and salts cannot reach the steel, corrosion is much harder to start. This is why pipelines are coated before being buried. Tanks are coated. Ship hulls are coated. Offshore structures are coated. Coating is extremely important because it reduces the exposed metal area. But there is one problem. No coating is perfect forever. Even a good coating can have small defects. These defects are sometimes called holidays. A holiday is a small area where the coating is missing, damaged, cracked, or not properly bonded. This can happen during transportation, installation, welding, backfilling, aging, or mechanical damage. and corrosion does not need a large exposed area. Sometimes, a very small coating defect is enough for corrosion to begin. Actually, small coating defects can be especially dangerous because corrosion may concentrate in one tiny spot. That can create pitting, and pitting can penetrate the steel much faster than uniform corrosion. So, coatings are the first defense, but cathodic protection is the second defense. The coating reduces how much current is needed. Cathodic protection protects the exposed steel at coating defects. They work together. A good corrosion protection system usually needs both. Cathodic protection is a method of protecting metal by making it behave like a cathode. Remember, the anode corrodes. The cathode is protected. So the basic goal is simple. Make the steel structure the cathode. To do this, we supply electrical current to the structure. This protective current changes the electrochemical condition of the steel surface. Instead of allowing the steel to lose metal at anodic spots, we force current onto the steel. That helps reduce corrosion. In simple terms, cathodic protection does not create a magic shield. It uses controlled electrical current to reduce the corrosion reaction on the protected metal. A helpful way to understand cathodic protection is to think about a battery. In corrosion, the steel and its environment can form small natural corrosion cells. These cells create anodic and cathodic areas. Cathodic protection interrupts this natural corrosion behavior by adding another source of current. We connect the steel structure to another material or to a DC power source. Then the protective current flows through the soil or water to the steel. The steel receives current and becomes cathodic. That is the basic principle. The first type of cathodic protection is called galvanic cathodic protection. It is also called a sacrificial anode system. In this system, we connect the steel structure to a more active metal. Common sacrificial anode materials include magnesium, zinc, and aluminum. These metals are more willing to corrode than steel. So when they are connected to the steel in an electrolyte, they become the anode. The steel becomes the cathode. The sacrificial anode corrodes instead of the steel. That is why it is called sacrificial. It sacrifices itself to protect the structure. Imagine a buried steel pipeline. A magnesium anode is buried near the pipe. A cable connects the magnesium anode to the pipe. Because magnesium is more active than steel, it naturally sends current to the steel. No external power supply is needed. The magnesium slowly corrodes. The pipe receives protective current, and the pipe is protected. This type of system is simple and reliable, but it has limitations. Galvanic systems produce limited current, so they are commonly used for smaller structures, short pipeline sections, well-coated structures, or areas where current demand is low. The second type is called impressed current cathodic protection, or ICCP. This system uses an external DC power source. Usually, the power source is a rectifier. A rectifier converts AC power into DC power. In an ICCP system, the positive terminal of the rectifier is connected to the anodes. The negative terminal of the rectifier is connected to the protected structure. This is very important. Positive goes to the anodes. Negative goes to the pipe, tank, or structure. The rectifier pushes protective current from the anodes through the soil or water onto the structure. This current makes the structure cathodic. That is how the steel is protected. Now imagine a long buried pipeline. This pipeline may be many miles long. A small galvanic anode may not provide enough current for that much steel, so we use an impressed current system. The rectifier provides adjustable DC output. The anode bed sends current into the soil. The pipeline receives that current. Because the rectifier can produce much higher current than sacrificial anodes, ICCP systems are commonly used for long pipelines, large storage tanks, plant piping systems, offshore structures, jetties, and large buried or submerged steel structures. ICCP systems are powerful and adjustable, but they also require power, monitoring, and maintenance. Let's compare the two systems. A galvanic system uses sacrificial anodes. It does not need an external power source. It is simple. It has fewer components, but it has limited current output. An ICCP system uses a rectifier and impressed current anodes. It needs external power. It is more complex, but it can protect much larger structures. It can also be adjusted by changing the rectifier output. So the choice depends on the structure, coating condition, soil or water resistivity, current requirement, design life, and maintenance strategy. In simple terms, for smaller or well-coated structures, galvanic protection may be enough. For larger or higher current structures, ICCP is often used. One common misunderstanding is thinking that cathodic protection replaces coating. It does not. Coating and cathodic protection are partners. The coating is the first line of defense. It blocks most of the environment from reaching the steel. Cathodic protection is the second line of defense. It protects the areas where the coating is damaged or missing. A good coating reduces the amount of protective current needed. A bad coating increases the current demand. That means a poorly coated pipeline may need a much larger CP system. So, in real projects, coating quality directly affects cathodic protection design. You may ask, how do we know if the structure is actually protected? In the field, technicians and corrosion engineers take electrical measurements. One common measurement is called a structure-to-electrolyte potential. For buried pipelines, this is often called a pipe-to-soil potential. A reference electrode is placed in the soil above the pipeline. Then a voltmeter is used to measure the voltage between the pipeline and the reference electrode. This measurement helps evaluate whether the pipe is receiving enough protective current. For marine structures, different reference electrodes may be used, such as silver/silver chloride reference electrodes. The exact criteria depend on the material, environment standard, and project requirements. But the basic idea is this. We do not just install cathodic protection and forget it. We measure it, we test it, we monitor it, and we adjust it when needed. Another important point. More current is not always better. Cathodic protection must be controlled. Too little protection may allow corrosion, but too much protection can create other problems. For example, excessive cathodic protection may contribute to coating disbondment or hydrogen-related issues in some materials and environments. So CP design is not just about turning the rectifier as high as possible. It is about applying the correct amount of protection. That is why surveys, measurements, and engineering judgment are important. Cathodic protection is used in many industries. You can find it on buried oil and gas pipelines, water pipelines, fuel pipelines, storage tank bottoms, ship hulls, offshore platforms, subsea pipelines, jetties, power plants, water boxes, and reinforced concrete structures. Anywhere steel is exposed to soil, water, seawater, or other conductive environments, corrosion can become a serious problem, and cathodic protection may be part of the solution. Let's summarize everything simply. Corrosion is an electrochemical process. It needs an anode, a cathode, a metal path, and an electrolyte. The anode is where metal is lost. The cathode is protected. Cathodic protection works by making the steel structure behave like a cathode. Coating is the first defense because it separates steel from the environment. Cathodic protection is the second defense because it protects exposed steel at coating defects. There are two main types of cathodic protection. Galvanic systems use sacrificial anodes like magnesium, zinc, or aluminum. ICCP systems use a rectifier and impressed current anodes. Galvanic systems are simple and do not need external power. ICCP systems are adjustable and can protect larger structures. Both systems use the same core idea: control the corrosion cell and protect the steel. Cathodic protection may look complicated at first. There are anodes, rectifiers, reference electrodes, cables, coatings, current, voltage, and electrochemical reactions. But the foundation is simple. Corrosion happens at the anode. Cathodic protection makes the structure, the cathode. That is the heart of the system. Once you understand this idea, the rest of cathodic protection becomes much easier to learn. In future videos, we will go deeper into sacrificial anodes, rectifiers, pipe-to-soil readings, test stations, reference electrodes, current requirements, and common CP troubleshooting problems. If this video helped you understand the basics, subscribe to the channel for more simple explanations about cathodic protection, corrosion, electrical systems, and instrumentation.